Hi folks, today we'll be using the VSEPR theory or the valence shell electron pair repulsion theory to help us determine the molecular geometry for a few polyatomic compounds. The one that we'll be examining are as follows: methane molecule, ammonia molecule, the water molecule, the boron trihide molecule, and carbon dioxide molecule. Below each of these formula here is the respective Lewis dot structure for the compound. Here you see it for methane. This one here is for ammonia. That is for water. That's for boron trihydride. And that's for carbon dioxide. Recall that covalent bonds are negatively charged because there's a high buildup of negative characteristics between the two bonded atoms. As such, if a number of covalent bonds are placed close to each other, because of their negative characteristics, they will repel each other sideways. For example, if I put these two magnets close to each other, look what happens. You see, they repel each other. In a similar way, the covalent bonds, if placed around the central atom, will repel each other as far away as possible to minimize that electrostatic force of repulsion between them. For example, if I have four covalent bonds here, four CH bonds, this is the arrangement that you'll assume. The carbon here is called the central atom, and these four hydrogen here are called the peripheral atoms. And each of these make a bond angle of 109 degrees. That's the farthest each of these can go. Okay, all because of the electrostatic force of repulsion between these guys here, okay? So when you talk about the valence shell electron pair repulsion theory, recall that there's a valence shell electrons that are used in bonding. So this bond that is formed here is from a pair of valence electrons shared by the hydrogen and carbon atoms, like these are the three, and they repel each other as far away as possible. And that is what determines the geometry of the molecule. In this case, it's a tetrahedron. The bond angles are 109 degrees. It's an AX4 type of molecule. All right? Now, look what happens. If one were to push these here, look what happens. They will not want to stay like that. What they will do, they will want to go back to that position there. Okay? So the next molecule you'll be looking at is the ammonia molecule. Ammonia is an AX3E type of molecule. So what we're going to do here is we'll transform that molecule to become like this molecule. How does it become like that? First thing we'll do is we will change the carbon to nitrogen. And then we have to contract this bond here. Then carbon goes to nitrogen. But one will show that this bond is still here. Okay? This is where this bonded pair was. So we take this bonded pair and you make it into a lone pair. Why I'm doing this? Because I want to show you that the position of this lone pair here is same as that where the bond was before. So you remove this one here and put a lone pair here. So a number of things have happened there. We have transformed carbon into nitrogen, and we have contracted that bond there that was a diffuse bond and make it into a lone pair here. This is now called an AX3E type of molecule. It is said to have a trigonal pyramidal molecular geometry. And the arrangement of the electron here is still tetrahedral arrangement. So the electron pairs are still, so here I have a bonded pair, three bonded pairs, and it's a lone pair here. So the electron arrangement is still tetrahedral. Another thing to note is that the bond angle here is less than the bond angle here. The bond angles here each is 107 degrees. Why? Because this lone pair is closer to these bonds here, and it is negative. It is pushing down these with a greater force than this one is doing there, because this is diffuse. This is close to the nucleus here, to these bonds here. That's why the bond angle is less. Okay? Next. We want to change this now to make water molecule. Water is said to be an AXE2 type of molecule. So how can we transform that into water? This is what we'll do. We had this before. This was ammonia. So it changed nitrogen to oxygen. But one thing we have to do now, we will remove one of these bonds here. We contract this bond here, and we make a lone pair here. So now, this molecule is said to have a V-shaped arrangement, or a bent. It's said to be a bent molecule. Okay? It is said to be an AX2E type of molecule. And point to note too also is that the electron arrangement, this bond pair here and that bond pair here, this lone pair here and that other lone pair here, assume a tetrahedral arrangement. You can see that, okay? So AX4 molecule will have a tetrahedral arrangement of electrons. AX3E will have tetrahedral arrangement of the electron pairs. AX2E2 will also have tetrahedral arrangement, but in molecular geometry is what is different. And also the bond angles. This will have 109, 107, 105.5
molecules
degrees. All right, I hope that was helpful. Now, we have to now do the BH3. Now you have boron with only 3 bonds around it. So these bonds will try to arrange themselves as far away as possible to minimize
the electrostatic force of repulsion
between these bonded pairs here. Okay, so the logical arrangement will be that where all of these bonds are 120 degrees away from each other, and this will be said to be trigonal planar molecule. This is said to be an AXE type of molecule. I'm going to ask a question. What would happen if you put a lone pair here? If you put a lone pair here, then it will squish these bonds down like ammonia. That is why it's very important. This is an AX3E type of molecule. And that is why it has a trigonal pyramidal arrangement. And this one is AX3 without any E, and therefore it's trigonal planar. Okay? Now finally we do carbon dioxide molecule. Carbon dioxide is an AXE type of. If you have 2 atoms around the central atom, the only logical arrangement for it to have arrangement will be a linear arrangement. So carbon dioxide is said to be a linear molecule. And the electron arrangement for this case will also be linear. So these are the molecular geometries for all these molecules here. You learned about electron arrangement. You learned about the bond angles. One thing more I'll tell you about. The cousins of these will be CCl4, CBr4, SiH4. This is ammonia. Cousins of this will be NCl3, PH3, PCl3. This is water here. Cousins of this will be what? SO, no, not SO2, OCl2, H2S. Okay? Cousins of this, one will be, this is BH3, BCl3, aluminum is the same group as that, be AlCl3. And this, of course, is carbon dioxide, maybe BeCl2, which is linear. So I hope that was useful to you. That is how we can transform this molecule into that one into that one, and so on like that. I hope that was helpful. That's how we determine the molecular geometry using the VSEPR, the valence shell electron repulsion theory. All it means this, that all these are valence shell electrons, bonded pairs, lone pairs, and what they do, they push each other as far away as possible, and depending on what they do with these peripheral atoms, that is what helps to determine the molecular geometry of these molecules. Thank you for listening. One point I forgot to tell you about. In determining the geometry of molecules, whenever double bonds or triple bonds are encountered, they are considered to be single bonds. As in this case, for example, you can see sulfur dioxide has a single bond here and a double bond here. That double bond there is considered to be a single bond. Similar to what is happening in carbon dioxide here. Carbon dioxide is having 2 double bonds. So we consider these to be single bonds. So remember that triple and and double bonds are considered to be single bonds. Also, a point of emphasis in ascribing what AX type of molecule we have, only the lone pairs on the central atom is shown. For example, in this case here, you have methane molecule, right? Here there is no lone pair. But in this case of ammonia here, there is a lone pair here. Why we need to put in that lone pair there is because it is the number of bond pairs here and the number of lone pairs that are repelling each other, and these are pushing these peripheral atoms in different directions, and that will determine the geometry of the molecule. Only the lone pairs on the central atom are shown. For example, again, in this case of water molecule, we are having 2 bond pairs and 2 lone pairs. And these are the ones that determine the geometry of this molecule. In this case here, for example, look at sulfur dioxide. Sulfur dioxide has only 1 lone pair on its central atom. But these here, the lone pairs on the peripheral atoms, do not affect these bonds here the way that they are pushed away from each other, that determine the bond angle and the geometry of that molecule. So when you are going to write the AX type for this, they look at the central atom there, how many peripheral atoms, and only indicate the number of lone pairs on the central atom. In this case, it will be AX2E type of molecule. Okay? Well, I hope that was helpful. Thank you for listening.